Welcome to Experimental Statistics Introduction to Sampling Techniques. In the first part of this course, we'll be reviewing several of the important topics that were covered in your first Statistical Methods course, which serves as the prerequisite for this course. The reason that we'll be taking time to do this is to make sure that we are all on the same page with respect to the terminology and the notation that we'll be using to discuss these topics throughout the course. In addition, and perhaps even more importantly, this gives us an opportunity to reinforce and even go a little deeper in our understanding of important statistical concepts that are often misunderstood, such as the concepts of p-values and confidence limits. The first topic in our review will be descriptive statistics. After that, we'll review the concept of the sampling distribution, which provides the basis for all frequentist statistical methods. As part of that, we'll also review the very important central limit theorem. Finally, we'll review several hypothesis testing and confidence interval estimation techniques for the type of sampling procedure that was covered in that first methods course, which in particular is IID, random sampling. And so now let's start the first module, which is our review of statistical concepts. And let's start off again by looking at what statistics actually is. So what is the field of statistics? Well, one definition says that it's the field of study concerned with the collection, the summarization, and the presentation of data, and the use of the resulting information in making inferences about the population from which the data were obtained. Now, in your first methods course, you covered three main areas in statistics. The first would have been descriptive statistics, learning how to calculate a variety of summary measures, how to create graphs that provide useful information, or how to organize data in order to glean some useful information from a data set. The last part of the course would have been the inferential part of the course, learning about inferential statistical techniques such as hypothesis testing and confidence interval estimation. In between those two broad areas of statistics, you would have learned some about probability. And that probability provides the linkage or the bridge between the descriptive statistics part of the course and the inference statistics part of the course. Now, in this course, we're going to have a short review of descriptive statistics. We're going to spend the bulk of the time, or the rest of the time, talking about various inferential statistical techniques, which depend on the type of sampling technique used. We're really not going to spend much time on the probability because you've already covered that in your first methods course. But I will say that we will do just a little bit of review on the concept of the sampling distribution and the central limit theorem, which understanding of those topics is critical. It's really important in order to understand inferential statistics. And in order to understand those topics, you need to know something about probability. So that is why in your first methods course you covered probability. It was for the purpose of understanding sampling distributions and so forth. Now, let's get into the first module, which is descriptive statistics. So descriptive statistics consist of methods for organizing and summarizing data in order to glean useful information from a data set, and methods for presenting that information in an enlightening and efficient way. Now, the method used will depend on the data type, the data level, and the shape of the distribution of the data. Inferential statistics is the use of sample data to draw conclusions about the nature of a population in order to answer various questions of interest. Now, in order to really understand statistics, it's critical that we understand the difference between a population and a sample. If we don't understand the distinction between a population and a sample, then really everything that one does in statistics will be a mystery. We won't be able to understand why we're doing it if we don't understand this important distinction. This distinction is especially important to understand in the context of a class like this, which is a sampling class, because we're looking at ways of sampling populations of interest throughout the entire course. And so we really do need to understand this distinction. So a population is, in a given situation, is the collection of all people or objects under consideration in a particular study and about which we would like to draw conclusions. A sample is a subset of that population. Now the goal of any kind of a research study is to collect a sample from the population, study the sample using the descriptive statistics that we have learned, and then generalize what we've learned about the sample to the population of interest. And so the question is, how can we do that in a valid way? That process is called induction, going from the specific results in a sample and generalizing those results to a population. And so what is the basis for doing this? That is where probability comes in. So the goal of inferential statistics is to study the sample and then generalize the results to the population. Now, what is the basis for this? Probability. Probability provides the basis for generalizing what we've learned from a sample to the population as a whole. And it also allows us to determine how reliable those generalizations are. So probability is what provides validity to this process of induction, this process of generalizing to a population what we've learned about from the specific data that exists in a sample. And so let's talk about data. All right, so a set of data or a data set is a collection of observed values representing one or more characteristics of some objects or units. So that's a very general type of definition. I'm sure that you're very familiar with data. You're probably performing experiments, performing studies where you're collecting data, where you're generating data. And so you have a very good idea of what data actually is. And so here's an example of a data set. And this is in a structure that is a standard structure. For example, in SAS, this is how a data set would be structured. In Minitab or in Stata and in R, we can think of this as a spreadsheet where the columns correspond to variables and the rows correspond to subjects or observations. So let's talk about observations and variables. Well, we have to talk about units, and so there are a variety of kind of units that we can talk about in the context of a data set in a study or experiment. One would be a sample unit or a sampling unit. Another type of unit is called an experimental unit. We might also talk about observational units. And so these kinds of units compose the information in a data set. Now, information from a unit is known as an observation. And so all of the values for all of the variables for a unit comprise the observation for that unit. And so that's what we're saying down here. That an observation consists of one or more pieces of information called variables. And so going back to this example data set, we see here, like I was describing, that the columns correspond to variables and the rows correspond to observations. Let me just point out here that one thing you can see is that some of these variables are numeric in nature, and they would appear to be inherently numeric. On the other hand, one of the variables here we see is got text information in here. All right, so this is obviously a non-numeric type of variable. And then we have the first column corresponds to, it is a type of variable. It's a subject identifier, and the values here are numbers. But I guess the question I would ask, do these values actually have to be numbers? Or could we uniquely represent subjects or patients or observations uniquely using non-numeric information? And so what this leads us to is looking at ways that we can characterize data. So one way to characterize data is by its type. And there are two broad categories of data types. The first would be qualitative data or categorical data, and the other type would be quantitative data or numeric data. And within the category of numeric data or quantitative data, we can further classify it as being either discrete or continuous. And so let's look at qualitative data first. So qualitative data measures qualities or characteristics of our experimental units. So for example, gender or eye color, or race or political affiliation or religious affiliation or any other number of qualities or characteristics that are not numeric in nature. On the other hand, we have quantitative data. Now, quantitative data is a type of data that measures numeric quantities. And let me just further specify here that in order to be quantitative, truly quantitative, the data needs to be inherently numeric. We can always utilize numbers to represent qualitative data. So going back to this spreadsheet here, for example, whether or not somebody has cancer, we can certainly use the text strings yes and no, as we've done here, but we could also use, for example, the numbers 1 and 2. So 1 might be no, 2 might be yes, or vice versa. And so in order for data to be quantitative in nature, it needs to be inherently numeric. Now, we can again divide quantitative data into two types. The first would be discrete. So discrete quantitative data is data that takes on a finite or countably infinite number of distinct values. And so, for example, if we were counting the number of hospital admissions on a given day, that would be an example of a discrete type of quantitative data. The possible values for the number of hospital admissions on a given day are the non-negative integers, 0, 1, 2, 3, 4, and so forth. The number of decayed, missing, or filled teeth. That's an example of discrete quantitative data. The possible values would be 0 up through the maximum number of teeth that a person has, and so that would be a finite set. Another example would be the number of dental x-rays an adult has had over the last 10 years. When I was on the faculty at the University of Kansas Medical Center, one of my colleagues in the Department of Preventive Medicine and Public Health, his research area was looking at the risk factors associated with x-rays and whether or not those kinds of things, whether too many x-rays caused cancer. So he was very interested in this kind of a variable, the number of dental x-rays that an adult has had over the last 10 years. So obviously that number, like the number of hospital admissions, it would be the non-negative integers. And then finally, if we were counting the number of automobile accidents in Baton Rouge on a given day, the possible values for that variable would again be the non-negative integers, 0, 1, 2, 3, and so forth. On the other hand, continuous quantitative data is a type of quantitative data that can take on any value in some range or interval of values. And so, for example, if we were measuring the height of a person or their weight, okay, those are inherently numeric and they're inherently continuous because there is not a finite or countable infinite set to which these values are restricted. Any possible non-negative value can constitute a height or a weight. In addition, if we think about age, and age when we're not actually truncating it, like we typically do when we talk about how old we are, but if we just talk about age in its true sense, well, we are all continuously aging, right? We're not aging discretely, and so age is, number one, it's an inherently numeric variable, and it's inherently continuous. Another example would be body temperature, all right? So temperatures are not just discrete values, but they are continuous quantities. A patient's cancer remission time, all right? So that is a time that a person is in remission from cancer, and so that obviously is another example of a continuous quantitative measure. And then finally, for example, a body mass index, that is also an example of a variable that is not only quantitative, it's not only numeric in nature, but it's continuous quantitative. Now, we can also characterize a variable by its level. And there are 4 levels of data. The nominal level, which is the most basic, it's the lowest level of data, it's the most basic level of data. Then the next higher level would be the ordinal level, and then above that we would have the interval level, and then finally the ratio level. Now, the nominal level is a level of data that is used to identify or categorize, but it has no natural or meaningful ordering. And so, for example, Gender is a level of data that is used to identify or categorize. But there's no natural or meaningful ordering. So we can characterize or categorize a person by their gender, but there's no natural or meaningful ordering there. We could also categorize someone according to their race. And so when people are doing health studies, maybe running clinical trials, it's very important to identify the gender and the race of people because, for example, if you're developing a drug, a pharmaceutical, then you want to be able to determine, is that drug safe and is it effective? And that often depends on a person's gender or on their race. And so you can have different safety profiles for different combinations of race and gender. You can also have different efficacy levels depending upon those kinds of characteristics. And so they typically would collect that kind of data in order to be able to make meaningful interpretations of safety and efficacy. We can also think of eye color. So that is a nominal level data or variable. All right, so you have blue eyes, brown eyes, hazel eyes, and so forth. So we can use eye color to categorize, but obviously there's no natural or meaningful ordering. You know, it wouldn't make sense to say that blue eyes are bigger or better than brown eyes, or vice versa. That really makes no sense, does it? All right, and so that variable, that data is a nominal level data. We could talk about state of residence. We could certainly categorize people by state of residence, but again, there's no natural ordering there. Telephone number, all right, we probably all have cell phones at this point. We may not have landlines, okay, but we all have a telephone number, more than likely, and those telephone numbers are used to identify us, and but there's no natural ordering. For example, it wouldn't make sense for me to say my phone number is bigger than yours, or my phone number is better than yours, or vice versa, your phone number is better than mine. That would be nonsensical. There's no natural ordering. So telephone, perhaps a better way to describe this would be a telephone ID, because really what we're trying to do, what it does is it identifies that device that you carry with you in your pocket or in your purse. So, but we all, we often call it a telephone number, all right? But it is nominal level data. And then as a final example, Social Security number or Social Security ID that uniquely identifies each taxpayer. Each taxpayer has a Social Security number, and the IRS uses that to make sure that you're, to keep track of your wages and other benefits and make sure that you're paying the appropriate amount of taxes. And so that Social Security number identifies you, but there's no natural ordering. Again, it would make no sense for one person to say that their Social Security number is bigger or better or whatever or smaller, than anybody else. So there's no natural ordering. Now, the next higher level of data is ordinal level data, and with ordinal level data, you could certainly use that to identify and characterize or categorize, but it has the additional property that a natural ordering does exist. However, the differences between data values are either undefined or meaningless. And so, for example, we might consider performance rating categories such as poor, fair, good, and excellent. There is obviously a natural ordering here. Fair is better than poor, good is better than fair, and excellent is better than good. However, the differences between these categories or between these values are undefined or meaningless. So, for example, what is fair minus poor? Well, we haven't defined that. It's not really defined. How about good minus fair or good minus poor? Is excellent minus good the same as fair minus poor? Well, those really are meaningless questions because the differences between these are really undefined. We could also look at risk categories, low, medium, and high. Again, there's a natural ordering here, but differences between these three levels or between these three values are undefined or meaningless. The next higher level of data would be interval data. Interval data certainly can be used to identify and categorize. It also has the property that there's a natural ordering, but it has the additional property that differences between data values are defined and meaningful. On the other hand, ratios of data values at the interval level are either undefined or meaningless. And so kind of the classical or canonical example of this would be temperature measured in either degrees Fahrenheit or degrees Celsius. And so, for example, if we think about temperatures measured in degrees Fahrenheit, let's think of a day in the summer where it may be 90 degrees Fahrenheit. And let's compare that to a day here in the winter when it may be 45 degrees Fahrenheit. Now, obviously, there's a natural ordering there. 90 degrees Fahrenheit is greater in temperature than 45 degrees Fahrenheit. In addition, the difference is defined and meaningful. The difference between the two temperatures, 90 degrees Fahrenheit minus 45 degrees Fahrenheit, is 45 degrees Fahrenheit, and so that makes sense. Okay, that's defined. However, the ratio of the two temperatures is really not, obviously we could do it, but it's not meaningful. So 90 degrees Fahrenheit divided by 45 degrees Fahrenheit, which, if we do the calculation, is 2, that value of 2 has no meaning. In particular, we cannot conclude that 90 degrees Fahrenheit represents twice as much heat energy as 45 degrees Fahrenheit. And so, and the reason for that is that the 0 degrees Fahrenheit does not represent a total lack of heat energy, all right? The same problem applies to temperature measured in degrees Celsius. If you have 100 degrees Celsius as compared to, let's say, 25 degrees Celsius, while the difference makes sense, the difference being 75 degrees Celsius, the ratio, 100 degrees Celsius over 25 degrees Celsius, which is 4, 100 degrees Celsius does not contain 4 times as much heat energy as 25 degrees Celsius. And so those are examples of interval level data, all right? Interval level data being a situation where differences between data values are defined and are meaningful, but ratios of the values are either undefined or meaningless. Then finally, the highest level of data, the ratio level data, this is where ratios are in fact defined and meaningful. And so, for example, if we were counting the number of hospital admissions on a given day, that is ratio level data. So, for example, if on one day there were 10 admissions and on another day there were 30 admissions, not only is the difference defined, a difference of 20 admissions, but the ratio is defined and meaningful as well. So 30 admissions on one day over 10 admissions on another day, that ratio is 3. And so on that one day where there were 30 admissions, there are 3 times as many admissions as there were on the day when there were 10. So that ratio is defined and it makes sense. Now, another example would be temperature, but measured in Kelvin. So for example, if we had 400 Kelvin, a temperature of 400 Kelvin, compared to a temperature of 100 Kelvin, well, the difference certainly makes sense. 400 Kelvin minus 100 Kelvin is 300 Kelvin. That difference is defined and makes sense. It's meaningful. But also the ratio is defined and meaningful in this case as well. So 400 Kelvin divided by 100 Kelvin is 4. And because 0 Kelvin does in fact represent the complete absence of heat energy, that ratio of 4 tells us that there is 4 times as much heat energy in 400 Kelvin as there is in 100 Kelvin. Okay, and then finally some additional examples. Weight would be an example of ratio level data, and also age would be as well. So if we compare the ages of somebody who is 30 years old to someone who is 10 years old, the difference being 20 years, that is defined and meaningful, but also the ratio is defined and meaningful as well. The person that is 30 years old has been around 3 times longer than the person who is 10 years old. So we can characterize data in terms of its type. We can characterize data in terms of its level. And finally, we can also characterize data according to the shape of its distribution. Now, the distribution of a data set is a table, a graph, or a formula that tells us the values of the observations and their frequency of occurrence. So that is what we mean by a distribution of a data set. The shape of a distribution is described in terms of its modality and its symmetry. So let's talk about these. So the modality of the shape of a data set refers to the number of peaks that a distribution has. So if a distribution of a data set or of a population in general has 1 peak, then we say that it's unimodal. If it has 2 peaks, then we say that it's bimodal. And if it has two or more peaks, then we can also say that it's multimodal. If it's got more than two peaks, obviously we wouldn't say that it's bimodal. It would be multimodal. We could talk about trimodal and so forth, but we would typically just say multimodal. All right, and then when we talk about the symmetry of a distribution, we say that a distribution is either symmetric or it's not symmetric, or we might say it's asymmetric. And so a symmetric distribution is a distribution where the left and the right sides of the distribution are reflections of each other. So if we think about a distribution, and if we think about some measure of the center of that distribution, and if I'm thinking graphically now, and if I were to draw a vertical line through what we might call the center of that distribution, if the left side is a mirror image of the right side, then we would say that the distribution is symmetric. We can also describe a symmetric distribution verbally by saying, or conceptually, by saying that smaller than usual and larger than usual data values tend to occur with similar frequency. All right, so that would be one way to describe or think about what's happening in a symmetric distribution, or what's causing a distribution to be symmetric, when smaller than usual values and larger than usual values tend to occur with similar frequency. On the other hand, if a distribution is not symmetric, then it's going to be skewed either to the left or to the right. Now, a right skewed distribution is a distribution where the right tail of the distribution is longer than its left tail. Now, what can cause this, or what's another way to describe this? Well, a right skewed distribution is characterized by occasional larger than usual data values. And so, for example, if we were thinking about income data, obviously there's a natural barrier, lower bound to income data, which would be 0. And then if you think about the incomes of the population of people who are working, there's going to be a lot of variability. A few people make a whole lot, right? And so that distribution of income data would be characterized by occasional larger than usual data values. And so income data is almost always right-skewed data. On the other hand, a left-skewed distribution is a distribution where the left tail of the distribution is longer than the right tail, and we can also describe this as being characterized by occasional smaller than usual data values. So those are the various ways that we can characterize data. We can characterize data by its type, whether it's qualitative or quantitative. If it's quantitative, is it discrete quantitative or is it continuous quantitative? We can characterize data according to its level. All right, remember we've got 4 levels, the lowest being the nominal level, then the ordinal level, then the interval level, and then the ratio level. And we can also characterize data according to the shape of its distribution. Is it a symmetric data set, or is it skewed either to the left or to the right? And we can also think about the shape of a distribution when we think about the entire population that we're talking about. And it's very important that we think about data using these 3 ways of characterizing data, because these different characteristics of data will determine in many situations the type of statistical analyses that we can perform. If we have categorical data or qualitative data, then we will probably use some kind of a categorical data analysis. On the other hand, if the data that we're dealing with is inherently numeric, if it's quantitative, either discrete or continuous, then we have a lot of techniques for analyzing data of that type. So for example, analysis of variance or t-tests or regression, things like that. The method that we use to analyze data will also depend on the level of the data. In fact, the level of the data is often more important or more of a determining factor than the type of data. And so, for example, if we've got interval or ratio level data, then we might be able to perform t-tests or ANOVA, regression, and things like that. But if we have data that is at the nominal or ordinal level only, for example, even if ordinal level data is numeric, then we may not be able to use some of the techniques that are typically used for quantitative data. So it's very important that we consider not only the type of data, but the level of data as well. And finally, when we think about the shape of a data set, and more generally the shape of a distribution from which, or a population from which the data is obtained, it is very important to consider the shape of that distribution. If the population is symmetric or fairly symmetric, then we might be able to use, and probably will use, techniques that are based on a normal distribution. On the other hand, if the underlying population is heavily skewed either to the right or the left, then we may want to look for a statistical technique that allows, or that is not based on, an assumption that the population is symmetric. Procedures based on normality, or assuming that the distribution is normal or nearly so, and that implies a symmetric distribution. But if we're analyzing income data, which tend to be highly right skewed, then we may want to use a different technique. So that is what I wanted to say about data and the various characteristics of data that we need to consider. In the next lecture video, we'll continue on looking at ways of more descriptive statistical techniques, and in particular ways of organizing and summarizing data in order to glean useful information from that data.